This. Hey, gorgeous, how are you?
Yeah.
Very good, thank you. Hi, Kaden, how are you?
How are you?
Doing good, thank you. There's some coffee in the back. The coffee in the back. If you want.
Got three. What kind of distracted? Very good. What's name? Oh, so. That's this. Coffee. Oh. That makes sense. It's using pressure.
Ah, Emma.
It's like literally squeezing it through its here.
How are you?
Just perfect.
Perfect.
Studying here. Not a problem. And there is a coffee on the back if you.
Thank you. Your chair. Yeah. Huh? It's not late enough. Close.
What do you think?
What do I think about what?
What are we going to do?
Today?
Yes.
4 to 5.
Lots of fun.
I am so happy to hear, but what is your vision of fun? Or what is your vision of my vision of fun?
Sure.
Would you approve if we call Kaiden to the blackboard and ask him to write something? It's a provocation. If you say yes, he'll be angry. If you become no, I will become angry.
Maybe I'll do it.
Yes,
Really?
Feels like the
yeah.
perfect,
Yeah, please.
as long as it's not the party.
I will help, and we all will go.
That's good.
So let's try, and everyone is very welcome to help and give hints. So energy of particle in the box. So E sub n. What Anna started. Agree.
Hmm. Wait, what is she writing?
He's so bad. That equation.
You got it.
Well.
Everyone is welcome to like give loud voices and help.
Over L squared. I thought, is it really? Over L squared. Yeah. That's all there.
Get this one.
It's your turn. I don't remember.
It's a candidate for retirement. Okay. What else?
Oh, better.
Is that what?
I don't know.
Oh, I'm guessing.
If if you're looking for dynamics, it should be also time, right? But we are looking on something different. Probably we should remove erase not everything, but this exponential.
You guys are a lot of help.
Yeah. Got it.
So let's think. Do not worry. Everyone will have chance to write something. You have a lot of writing. But Emma is the bravest of the class. So there is the index n. Does it come into the expression? How?
Not in an exponential.
That is for the index.
Just let's listen to the common wisdom.
Index is eigenspace.
S squared?
As a square, it's n squared.
N squared?
N squared.
Perfect.
Yeah.
Great class. I was like, wasn't.
Okay. So the rest is boring. If someone doesn't want to write the rest, it's okay. So it's something like h bar squared, pi squared somewhere, maybe another factor either here or there, but we do not worry of this so much. You wrote most important things. So it's inversely proportional to L squared and directly proportional to n squared. So last thing you do before relaxing.
Oh.
Suppose that it is a box in the dimension of x-axis. And later on, we are going to look onto boxes in different directions. So what should we do to underline, to highlight that it is an x? So 0 to, if the size of box in different direction can be different, should we call it L sub x? And the quantum numbers for x and y and z can be different. Can we reflect it in the equation? N sub here. Perfect. Let's thank Emma.
That was awesome.
Crazy.
That was sick.
I was so accurate.
That was like
So if yeah, just try to do the same and replace an x with an y. and like do everything for y direction. And if anyone finds errors or corrections for these factors, please let us know.
Over 2M. That's the other.
Yes, correct. Thank you.
What is it? Oh, wait. Is that H?
It's a little easier because your colleague has established a pattern.
That's how it starts. You're off your rock right now. You're capping.
Okay, so what is important? That the size of the box in y direction can be different, and quantum number in y direction can be different. Excellent. Let's thank Anna. Spencer.
Spencer. Yes.
So would you be able to write an equation for energy for z direction? Let's try.
Same thing you just.
Okay, let's thank Spencer. Yeah.
It's Spencer.
What? So I like to hearing that you anticipate force direction, but let's think a little more practical. Force direction is too much.
Okay.
3 is enough for our simple world. But right now we are coming to most important philosophical part of our discussion. The rest will be just rolling downhill, exploring the same idea. So I don't know how to formulate the question, but what is a different if you want to ship by FedEx a downhill ski, what would be the shape of the box? A ski for downhill skiing? What would be, just show how the box will be shaped for your draw?
If you want to go downhill on ski.
Yes, and you want to ship this ski to a friend in Seattle. What would be the shape of the box? Long. Okay, good. Okay, you decided that your friend doesn't deserve so generous gift. You decided to send him just a box of pizza. What would be this? Can you draw the box for pizza box? How does it differ? But it's skinnier. But right now, Wyatt is doing 2-dimensional drawing, right?
Yeah.
But we are doing 3-dimensional world, right?
Yes, you want to have
Yes, yes. Yes, yes. Perfect, perfect. And I don't know if the following will be poor joke or a good joke, but if a person A wants to establish an engagement with person B by mail and sends a diamond ring in a box, what would be the shape of the box on the same scale? And it is 3-dimensional. That's perfect. So now, what is the difference between these 3 boxes?
Size.
Volume, size, length, what else?
Mass.
What else? Okay, what else?
Shipping price, package fees.
But for you as a artistic design drawer,
Yes.
what if suppose I'm your fellow blind scientist on the other part of the world and you want to teach me how to draw these figures?
Okay.
How do you explain me what to do?
Okay. Okay. So for
We're gonna start with the ring.
Okay.
So the ring ones draw like a tiny little square.
But how long, if I can do just a line first, how big should be the
Think of
line?
it as like a centimeter.
Okay, so Lx equals 1 centimeter. Okay, what else should I do next?
Are we doing height now?
Uh-huh,
Okay.
just direct me.
Height is, think of it as like the same height.
Okay, am I putting to the origin,
No,
to the left, to the right?
and on the, why put the marker on the line?
But you can just give me commands, up, down. Okay, so 1 Ly equals also 1 centimeter.
Okay.
And now I do a square, maybe it doesn't look like a square, and now I do Z direction. And I put in LZ equals also 1 centimeter. Now, when I turn around, I probably will be very surprised. But sure, but you need to make differences between these three images. You need to tell lengths of boxes in each dimension, in each direction.
Yes.
So Lx, Ly, Lz, right? They have different aspect ratio, right? So you put Lx, Lx, Y, Lz. For the ski, Lz is much bigger than Lx, which is about equal to Ly. For pizza box, your Lz is equal to Ly, but much bigger than Lx. For the ring box, you have Lx equals Ly equals Lz and goes close to 0.
Yes.
You agree?
Yeah.
Okay, so you mentioned many parameters, but for drawing, it is just aspect ratio in X, Y, and Z. Excellent. Let's think quiet. Curtis?
Picture of the guy just like a light photo, you know?
So can you, I do not know how to formulate a question. Can you just write add all three together and write what it is equal to? No, just add. Energy is multiplicative. Wave functions are I cannot pronounce. Multiplicative. And energies are additive. Just add together as it is written. E and with a little more space here. So the common factor pi squared h bar squared over 2m can be put outside of the brackets. Okay. Excellent. Maybe in this way a little better. It's maybe upside down, but we are so artistic that we can imagine what is being written. Okay, so it is in nominator, not in the denominator, right? Size is in the denominator, quantum number is in nominator, right?
Oh, yeah.
So can you just explain, because some of us were sleeping, drinking coffee. what did you draw?
So when you add them together, you can put the common factor in all of them, so you can just pull that out. And then you can just add all the unique terms together. And it's multiplied by the common factor.
Okay. And then if it is one quantum state composed of 3 dimensions, one can tell that it is one energy, but with 3 quantum numbers, and X and Y and Z. You approve? Okay, let's thank Curtis. Thanks. Will you come forward? So just tell what do you think about it before writing anything.
I thought that.
So what three indices, so maybe we can arrange it in a matrix, or maybe it's a tensor.
But can we put size of the box outside of the bracket?
Outside of the okay.
We can or we cannot. You just if the sizes are different.
No.
We cannot. So what is the meaning of the size of the box in each direction? How would you interpret it?
It's the dimension which belongs to the general.
Yes, but if you are thinking about energies, what is the practical meaning of the size of the box in a certain direction? Like if we have nx squared multiplied by 1 over x squared. So what is the meaning of this factor as we go from quantum number to the energy? It's all very simple, very basic, but it is hides the whole nanotechnology is in the answer that James is going to give.
The smaller the dimension goes, the greater the difference between different energies.
Everyone agrees? And opposite, though.
The bigger the three-dimensional space the electron occupies goes, the smaller the difference between the energies are.
Okay, so we have the same progression of quantum numbers equals like an x equal it z 1, 2, 3, 4. But by changing size of the box, we have different energies. So size of the box defines scaling,
Yeah.
proportionality coefficient between quantum number squared and energy.
Yep. So they'll be a lot closer together with a much bigger area.
And this proportionality coefficient can be different for each of the dimensions.
Some scores. So
Oh.
yeah.
Okay.
But if we want
Let's do a little exercise, what you've called tensor. Maybe let's do it on this board so that we do not erase things. So and x and y and z, and then let's assume that pi squared h bar squared over Lx equals Ly, Lz equals L, and this all equals to 1. So under this condition, let's put energy and X and Y and Z for first, let's say, I don't know, four quantum states. Can you just fill the table? Start filling the table, and then we'll have help.
L equals 1, L equals 2, and then
No, first you start the ground. The lowest state is when each of the dimensions is in the ground. Let's put it as a table, like 1, 1, 1, 1. Energy will be and 2m, so that we do not have, let's put 2m here as well, so that we do not have any dimensionality issues. Yes, 3. Okay. You're following what he's doing.
It's taking me a little longer.
No. It is nothing wrong, but we want to be systematic. like as a human, if suppose perfect. Like I cannot go in 3 dimensions simultaneously, right? It will be a dancing contest. Oh, you're too far. You're too far. Let's slow down a little bit. You're doing everything correctly, but we can be more systematic. Let's. Those will be different quantum states, right? Yes, go ahead.
What is he using for L? Oh,
I did set it up here so that all factors together equal to 1.
Oh. Yes.
oh,
Is L there? Oh, L.
Yes.
Okay,
So what do you see? I think it is the amount of table for one person is enough, but what do you see? First energy is unique. And what about next 3 energies?
They're all the same.
Yes, let's thank Jeff. English is not my native. When I was a postdoc at the University of Washington, there was a secretary at the department who was probably from high society, and I've asked her as a native speaker to proofread an abstract that I was sending to a conference. And she was very gentle. She said, you know, some of your wording may be not appropriate in the right society. What? It was scientific. You know, it's a word that used for people who are drinking alcohol, do not have a good pedigree. What? And then I realized that it was a scientific word that is used to describe this situation. So in common language, it is used for like lower slice of the society or person with people with birth defect or something like this as a bad word. And here it is used just to say that several states have the same energy. Huh? Would be more polite. The word is a little bit more rude if used. If one person calls another this word, it's definitely an offense. Much more offensive. Dumb is some okay. It's like if I tell to my cat, "You are dumb, you are silly," I'll pet you. It's okay.
Yeah, Gen Chem. We also
Degenerate.
Huh?
degenerate.
It's degenerate.
Yes.
oh, the gem.
And your version was
But I don't know if that's
good. But degenerate. So the first excited state of 3-dimensional box is degenerate if the sizes of the box are the same, right? It is important. We will return to this point. But 2 double letters. Got it. Please continue the table.
That's how you want to.
Mm-hmm. Okay. 2, 1, 2. Okay, keep going, keep going. Okay, maybe one more.
One more.
So you see, second excited state is also degenerate. Well, if I there's a coffee. What confuses you?
So you want me to go?
Okay, and what will be the energy? Okay, and if you do another experiment, if you do 3, 2, 1, would it be smaller or higher or lower? Okay, let's then put it inside before so that they are ordered. Yeah, here, ordered in standing order. What about 3, 1, 1? Oh, then they should be swapped, right? 3, 1, 1 it goes everywhere, and then
Yeah.
good. Enough. Let's thank Gareth.
The numbers in the last column.
Would you
It's the sum of the squares of those numbers. So 3 squared plus 2 squared plus 1 squared, so 9 plus 4 plus 1.
do you just take this equation and plug in values and x and y and z, right? Oh, now I have a good idea for quiz or homework. So maybe I'll do a little correction, and then Kaiden, and then Ifani will help me. So I am going to erase once again 2 to 2, 3 to 1, 12, 14. 3 to 1, 3 to 2, and here we will have another degeneracy. 1, 3, 1, 1, 1, 3, 11, 11. Right? So again, triple degeneracy. Eden, would you please continue? There is not much space, but
Let's do those last two.
try to squeeze there another 100.
Other side.
It's a sign of nobility. I've got it professionally.
On the other side.
It can become worse. Look like ready for a chief ready for intervention. 15, 17, no 14. And how let's do a creative thing together. So now you all remember the word degeneracy, and you remember having it in the past. Let's add another column here and put degeneracy. So here it's degenerate once, here it's degenerate triple, here it's degenerate triple, triple. And now instead of repeating all possible, can you tell what would be the degeneracy of this energy?
The 3, 2, 1.
Uh-huh. Any opposite opinions? But we will repeat this the 17 later. What about 1, 2, 3, 2, 3, 1, 1, 3, 2. Keep going. How many times you can repeat, combine the three numbers?
Permutation NR is n over r factorial 1 minus r factorial n minus r factorial.
Mhm. But simpler. What is the answer?
It's like 5. Or excluding the ones on the list, it's 3. Are we allowed to say like 2, 2? No.
No. Let's try once again here. So 1, 2, 3, 1, 3, 2. So we swapped this one. Now we swap this two. 2, 1, 3, 2, 3, 1. And then we swap this two. It will be 3, 2, 1, 3, 1, 2. I count as 6. Is there anything missed? Nothing is repeating. They all are individual, right? Are there more combinations? Did I miss any? So two combinations that starts with 1, two combinations that start with 2, two combinations that start with 3. Total 6. So it's right down. Yes. Okay, let's thank Kaiden. Thank you. If any, would you come here and help us? So we were trying to plug in numbers into this equation. Can you just share? You don't need to write if you don't want, but can you tell how do you interpret what is written? And yes, this equation. What is it?
Energy number for X equals energy number for Y.
So this energy of quantum state with 3 quantum numbers. Yeah. And we just swap different values of these quantum numbers and explore what is the value of energy, right? Okay, let's thank you, Fanny. So repeating the same question to Emma. Your opinion of my opinion of having fun during the meeting. What do you think? I've asked you what we will be having during this meeting, and you've told we will be having fun. Can you tell your vision of what fun is? Or just summarize what we were doing, what's used for agriculture, medicine, and industry.
Trying to think of like how.
Or why it is different? This question is. Answer something.
The dependence of the energy based on how far we go in each axis or in each direction. Degeneration depending on which, like the amount of, no, the length of our box in each axis. I'm really trying. I'm really trying.
You're telling everything correct. I know it is hard, but you told 0 wrong information. Everything was correct.
Perfect.
Anything to add? Let's pass on to Anna. Yes, let's upload. So, just your vision of what have you done? What is the benefit?
So kind of like how Emma was saying, like it's the different lengths of the axis of like the box, and like for the degenerate, like it gets, for the dimensions, it goes up the higher the dimensions are.
Here is one aspect. It is if sizes in each dimension are different. But here in this example, we assume that sizes are the same.
Yeah.
Then proportionality coefficient between quantum numbers and energies are the same for each dimension, and we are getting to the effect of
Degenerate.
Yes. Yes, that's great. Oh, would you allow me to erase? Do you remember these things? So it's not yet. No. So we do have a table, right? We can play a little orchestra. Each individual person have a different size of resonator, right? And it will be a different tone. Like if everyone does it. And then if anyone asks what are you doing on physical chemistry, we have a strict answer. So E111. And we know that for this example, how much was it? 3. The next one was E122, and the value was 6. E122 multiplied by 3 degenerate. Next one was how much? 9. 9. How did we get it? E122. Also with triple degeneracy. Next one was 11. And how do we call it? E311. 311 with degeneracy 3. Next. 14. Okay. And it was E123.
Yes.
Okay, enough. So energy and X and Y and just energy. Now, can we put degeneracy on the Y-axis?
Of course.
So 1, 3, 6. 1, 3, 3, 3. This one is 6, right? I would love someone to tell next few sentences instead of me, but let me do it. The offset between these energies, the bigger, the smaller the box, or the smaller, the bigger the box. Box is, we were discussing, it's like a piece of semiconductor or maybe a oligomer of different lengths, right? So if you take very long oligomer or very thick piece of semiconductor.
Big box.
Big box, yes. Then energies will be
Closer together.
yes, right? Suppose we work in material science discipline and we want to characterize ensemble of identical objects, nanostructures, of the given form factor, of a given aspect ratio, given size. and we want to tell their like spectra, how their energies behave. So if it is a very small object with very sparse energies, we just can give a list as we did on the board. But what if the object becomes big? How can we characterize energies? So if the object is big, energies become dense. I apologize for this childish assignment, but just please repeat after me the last sentence. Energy becomes dense.
Energy becomes dense.
Thank you so much. So now we come to the concept of the density of states. Repeat, sorry. Concept of
Density of states.
Yes, thank you so much. So density of states. Oof, states. So these, like, if you have a scaling factor, if you have units here, and we redo the same thing with a bigger box, the figure will look like the same pattern, but they will become denser. If it is bigger, they will become denser. And finally, for human eye or for instruments that we have in labs, they will become indistinguishable, right? But we do see a trend that at the beginning or density of states, they are not as dense because of degeneracy, and then they become denser. So if they merge together, it will become a continuous function that just grows, right? As we go higher in energies, there are more and more energy states. Good. Now, how to do it mathematically? How to do it more rigorously? Because what I've told right now is more like hand waving. There are two ways. One that we do not need now, that we will do in class on Monday, is to set up number of states with energy less than a threshold. Number of states for certain energy interval. I'm just telling it for information. So for if there is an energy interval, delta E, and then we have a number of states as size of energy interval, and then if you take derivative of number of states over the if you increase this delta interval, it will be density of states. So if we go further in energy, what would be the derivative of this total number of states? If the area under the curve is number of states, then the derivative will be the actual line. If you disagree or to argue, I'm very welcoming. But we will devote basically Friday and Monday to this subject. So if you may either ask now or postpone, develop your questions and postpone. Second way. I'm so impressed of the second way. I just cannot breathe and excited of how beautiful it is. And how brave and unusual it is. So right now we were putting sticks, right? Just to symbolize the higher the stick, the higher is degeneracy. You can think that it was like maybe matches, right? One little stick. But then if there is degeneracy, we can tell degeneracy 3, we can put 3 little objects to the top of each other. It became triple higher. So it's all human intuitive. So instead of these objects, let's put our preferred mathematical object, Gaussian function. So let's replace a stick with a Gaussian of certain width. Then here we will have 3 Gaussians on the top of each other. So it will have just taller, right? With the same width. Same here, even taller, right? Good. But what would, and here in this image, we have energy offsets between individual Gaussians bigger than their width. By the way, width is related to thermal broadening because there are no, if you are not, even if you talk about absolute energies, there are zero oscillations. So interaction with heat, oscillations of ions contribute to the width that there is uncertainty of electronic energy. And it is the meaning behind this uncertainty and distribution of the widths. But if our system is so big that the energy becomes so dense that we need concept of density of states, this Gaussian peaks will start to overlap, right? And if we mathematically add together all Gaussians, we will get more or less continuous line. Got it? So now how to write it down? If I will write down the whole Gaussian expression with normalization, exponential, it will be correct, but boring and long. In case the width is going to zero, it is common to assume delta function, which is equivalent to Gaussian with zero width. So energy minus energy of nx and y and z. So the delta function will have a peak at when the E value on E axis is equal to the computed value of energy there. And then we put summation over nx, summation over ny, summation over nz, right? And call it density of states as function of E. If I would have a little mirror with me, I can read what is here. So, questions, objections, discussion.
Big E.
Huh?
What's the big E supposed to represent? The one without the NX and Y and Z by.
So the question of James was, what is the meaning of big E, right? The eigenstates, eigenenergies of a model do exist independent of us humans and our attention to them, if we are theorists, or independent of our instruments applied to these objects. But if we design an instrument that will scan through all possible energies, so it will tell parameter E tells how many energy states we have at energy interval in the vicinity of this value E. So it means we scan different values of E and then define a function, like what is the probability, what is the amount of states in a given vicinity. Like it's nothing bigger, 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 or nothing, something, nothing, something. Right? So it is a scanning parameter, and a lot of experimental instruments, such as spectrophotometers, are designed exactly this way. They measure not literally density of states, but like spectra, which are density of excited states multiplied by oscillator strength. But the philosophical idea is the same. Like how you, in the spectra, which you all know, right? You take a prism or a diffraction radius and decompose the white light onto components. And then you plug in your molecule and see how it absorbs or emits at each of these decomposed parts of the spectra. So what is the parameter in the spectral decomposition? It's just parameter of wavelengths or energy. It's a way how we scan possible energy states. James, does that answer your question?
So. He's not on the x-axis, or is it on the x-axis?
Is on the x-axis. So E is x-axis, and this E sub something is a special points on the x-axis. When value of E is equal to the special points, then the function of density of states will have peaks.
Oh, okay.
Okay?
That's,
Better.
that's just throwing everything out that doesn't have meaning.
Mhm.
That's what that means. It's an exclusion of the meaningless garbage.
It is. It's not wrong, but I would say it is just a tool to scan all possible values of energies.
It's like denoising kind of.
No, not so far. You in this summation, we include all possible energy states, right? Literally. But when we plot a function at each point of time, we have only one value of energy. So we pick certain range of the whole dependence at a given data point.
Oh, so it's the density of states for that certain set of energy values.
Remember, at this place, there was a expression for energy of three-dimensional box as function of nx and y and z. Okay? This is a way to represent all energies of three-dimensional box in a one plot, right? So here we show these same values of energy as we did show in this table, and one can go further, and so it is one continuous plot that covers all energies, right? Make sense? Agree? Disagree? More comments? Yeah. Okay. So please open something. I mean, computers and then emails and the codes. And let's look on the code named
No. 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 No.
so DOS underscore 3D A. So let's
Are you serious?
run this code and see what happens. So we stopped our section of interviews on Anna. Now we'll continue with Ifani. So run the code, look what it is, and we'll be doing a little interviews. Just run it and see what it generates. There is a little coffee refill in the back if you are drinking coffee at evenings. Please. You're welcome to.
Black body radiation. Kind of interesting. This is in jail. Why would it do this? Real. Increase. Oh. Oh, we didn't have to do that. What the dog? Stop. What the dog? I have a T-pose right now.
Stop. Don't make
T-pose right now.
Don't.
Right now.
Stop.
It's a graph that shows the stimulation and the theory between energy level.
Did that in the middle of the room.
Yeah.
Everybody saw, the camera saw you do it.
Do you accept answer? If any? You didn't hear.
Did not hear.
Shows the theory and simulation of between energy levels and
So like, what is x-axis, what is y-axis? How do you interpret? Or how do you guess what it is? Like, what is x-axis? What is x? Yeah.
X
Uh-huh.
and the Y.
Yeah, what is x, what is y?
3 and 5.
No. Not what are the numbers. What is which physical value, which observable is based on x-axis?
Okay.
Just read what it is. What is on x-axis?
Simulation
On x-axis.
is the energy.
Yes, it is energy. What is on the y-axis?
The number of
So DOS. What DOS stands for?
density of states. Okay.
Yes. Okay. Yeah. Thank you much. That's perfect. Do you want to ask any question to the next speaker? No. Okay. I don't know what to ask, but why there are two lines?
One is like, looks like one is more of like a theoretical limit, or you were saying if you like squish them together or something that they make just a straight line pretty much. I'm assuming that's what that orange dash line is if you combine everything. But the blue line is more of like the practical like Gaussian wave.
Okay. Do they coincide or diverge? Will they coincide in one area and diverge in another one?
They coincide to begin with, but then diverge.
Okay. Okay. That is what do you want to hear? Thank you. Yeah, that's about. So wait, let's do an experiment together.
Okay.
Let's go to the code itself and find lines from 5 to 6 and remove these zeros.
Okay.
Save and run. And I will not show you, explain what do you see. If you have a little bit bigger. So just let's
I don't look too good.
Oh wow. Oh wow.
so we can instruct others what to do because everyone is confused. And then
Oh, I didn't know what you did with the keyboard here though. I didn't know what you did there.
What you think you forgot? Sorry, you missed that. Why was doing ASMR?
Why was doing ASMR?
He was like eating the mic.
What the?
Oh, what the hell? No, okay, yeah, you know what I meant. Oh, we don't.
I'm getting fussy.
You amazed me so much. More stress you have about my life.
okay, just because everyone else in the class is confused. Or you can do it on this podium.
Okay, so first step here. through the lines 5 and 7, I want you to get rid of the zeros.
Okay.
Get rid of the zeros first. Once you're done with that, hit save and then exit out of your old figure because you're gonna get something new and it's gonna look a little different, but we're gonna change it to make it completely different. And you'll notice that once I tell you the next instructions after that.
Okay.
Okay.
I did it.
Okay, you guys got it? Okay. Okay. Next thing, I'll do it on here and I'll give it an easier. Okay. Okay, next thing, you want to hit the little icon here, and then I want you to click on the line. Should do it, and then backspace. Oh, did I do it? What did I? Okay.
What did do?
Really jittery.
I'm just getting going. I'll start. I have a bunch of points on all. So it's so you double clicked. Ow. This is great.
It's just not working.
Yay, I can command Z, let's go.
Because this is what it takes to be.
What the actual fuck? What the? What happened with me?
Okay. When when you click on the arrow and you click on the line, you're supposed to get dots on the theoretical line here. And then if you see those, make sure you hit delete or backspace. Because when you do, isn't the line supposed to go? You're supposed to get a really squiggly line.
Oh, like this?
Yeah, like that, like what Spencer has if you look at his screen. That's what you're supposed to get.
I'm confused.
Okay.
Why do it again? Show me. What'd you do? I did that and it just got rid of it.
Okay, get into the window.
I'm in the window.
You're in the window,
I'm in the
right?
window.
There we go. Yeah, you're supposed to get this. That's what you're supposed to get.
And now backspace. Yep, you didn't hit.
Okay.
Yeah, for sure.
What does DOS mean?
Density of states.
Density of states? Oh, sorry. Thank you.
Yes. Crazy.
From what I can interpret from looking at this graph is that when the more energy you have, the higher your density of your states is going to get. And then I think you get more of it, or does it like repeat? Because I mean, it kind of looks like it repeats, but it gets higher. But I think you get more density of states.
I think the simulations, guys.
I think it was perfect.
Oh, let's go.
Yeah. Next time. Let's go and keep teaching the class.
Okay, what a dog.
So, please inform a comparison between our consideration here, maybe for first 3 peaks and the peaks there. You see similarity.
In this one,
Yes.
it looks like it just goes higher. And then this one, it goes higher, but also has points where it goes back down.
Okay. But let's discuss one with first and second peaks.
They're identical.
Would it be correct to say that the second peak is about 3 times higher than the first one?
Yeah.
So it is a signature of.
Degeneracy.
Yes, I think. Yeah, okay, thanks. So James, let's do an experiment together. You do something and then you see others. So make B, you want to set up so that the values here will be absolutely the same. Make them all 27 or all 26, and then rerun and see what will be the consequences.
Nope. Didn't work. Hold on.
And then you do the same thing with truth visualization.
Oh, that's a much nicer looking plot. Oh, yeah.
You can go
My horse.
put this here and expect it.
Alrighty then. Did that. Hold on. Oh, well, never mind.
It's just
No, I heard.
Okay.
No, I was joking. Now I feel like it's very.
That on? Yeah, it is.
So I think Angie,
Here we go.
I'm making it hurt.
Okay. So everything looks a lot nicer. We have 3 3s. And we have 1 6.
and there's something in between. And just is the signature that because it's something in our table. What was feeling this table?
There's 12. There was a value, there was a couple values for 12 in there, it looks like. That we didn't include because 2 2 2 and 12.
Okay. Okay.
So it looks like that's our funny delta function that slaps peaks everywhere there's degeneracy.
Okay.
Is that it?
Fine, or you have questions, James?
No, that's wonderful.
Really?
It's 2 2 2.
Was I right about that delta function thing or was I wrong about that? Is this graph here the delta function that slaps peaks everywhere there's degeneracy?
Yes.
Okay.
Okay, let's thank James. Let's pause the microphone.
I know.
Right. Let's do an experiment together. You do it here and then you comment and explain to everyone.
Sounds good.
To repeat this. So this little offset of sizes is to artificially break the degeneracy, right? And now let's slowly get away from our setup. Like 26 is really a small number, right?
Yeah.
260 is something big, right? So let's just add 1 0 and keep others as is and see what would be the consequence.
Space. All right. It's very a lot of peaks and they're not symmetrical. They have shoulders, which means
Let's please do it in here and explain to one of you.
Okay. Okay.
You run it?
I did. Oh. Right. Click the line, click backspace. There we go.
Okay. So teach us what do you see. First, maybe you are the instructor, but I just give a little suggestions. Kaiden was teaching us, no, not Kaiden.
No.
Everyone was teaching us something new, but Wyatt was teaching us about the difference between pizza box, ski box, right?
Yeah.
Which box do you describe right now?
This is the ski box.
Yes, I agree.
Perfect.
But what are your observations? Just as if you, I don't know, you see yourself as theorist or experimentalist, but both parts of science need to describe what figures look like. What do you see?
I see
a lot of peaks. They're not as distinct as they were before.
So they're
Um,
broader.
They're broader. There's a lot more overlapping. And you can see that since some of these have these shoulders here, right? It's a little broader on one side.
Let's give one more applause to Garrett.
Thank you. Thank you.
Shoulders. So if we put a middle line, would this peak be symmetrical, unsymmetrical in respect to middle line?
Asymmetric.
Asymmetric, right?
Mhm.
It's shorter on one shoulder, longer on another one. It is a great discovery, and our whole Friday meeting will be devoted to prove it mathematically.
Mhm.
We will see that it is not a random coincidence of stars for this simulation. It is a like universal fundamental law.
Right, because this peak could be decomposed into the one large peak, and then the shoulder is made up of different peaks.
Okay. So before we were thinking that the higher the energy, the bigger the density of states, the denser the states. Here you see that you get to higher energy, and until some threshold, energy density of state decreases. How would you interpret it?
You're saying as the energy increases, the density decreases
Yes.
in that region.
Yes. Isn't it a strange?
Yes.
Challenge?
I don't know.
Go forward for your Nobel Prize in nanoscience.
I don't know how to interpret that.
You all have the answer.
In this small region, say we were just looking at it here, we see as energy increases, the density of states increases, and then it starts to decrease. And he's asking us to interpret that.
So how do we interpret the observation that in some circumstances, in some interval, increase of energy leads to decrease of density of states? And I claim that you all have an answer. More than half of you were even writing the answer on the board today. It should be in your active memory.
Like that big box. Electron doesn't like that box.
No, electrons sits in the box.
I'm guessing degeneracy.
So degeneracy was high, and now it is getting low. Very good idea. It's not wrong. It's good. That's very close to a cloud, as a halfway to the answer. That's okay. You'll go another road of way to it.
Are there more of the same energy state?
More energy states in the interval when we have dense, but less when we have density states is lower when there are less states per energy interval.
So does that mean that there are more like of the NX, NY, and Z that there are more occurrences of the NX and NY and NZ having similar numbers between them? Like
More occurrences with similar number here and less occurrences there.
Oh,
You do. Let's
yeah, get me in the zone.
and even erase the statement that yours. Yeah. Erase it. Now I will give a really hard assignment to Garrett. Everyone can do it, but he will do the major part of the work. So it will be two parts. First, write down an equation for energy of a particle in one dimension. Not three dimensions as we did before, just one dimension. Emma started. Yeah. That's already was left. Yeah, much I was watching a comedy where one of the character was a cop. He was in a coma, and his friend wanted to bring him out of coma. And the joke was just put a gun into his hand. He will remember who he is, and he will wake up. And they failed because they were putting it into right. And as soon as they realized the left hand, he woke up and go on. So, and if you still believe in dimensions, yes. Now, let's put energy, not everything, not here, you know, put weight or density of states, and let's, it's only one index, right? Let's put there on this axis E1, E2, E3, E4. But I put them here as a list, but they will have different energies. Can maybe E divided by everything except an X. H bar squared by squared to LX squared. Yeah. So dimensionless energy.
Just n squared.
Right. Please do it. We all know the answer, but no one was interpreting the line for it. So let's do small steps.
So you want me to plot it or just
Yes.
write it here? Okay. So we're just doing n squared, so 1,
Okay.
and then 2, oh, 4.
Yes. So and we let's start a little early. 1, less than 2, less than 3, something is 4. Just do a little bar.
Wouldn't it be
E2 equals 4, right? Yeah, and it is not
okay.
degenerate. For one dimensional box, it's not degenerate.
Okay.
Okay. And then you're following what we are doing, right? 5 empty, 6 empty, 7 empty, 8 empty, 9. Okay, keep going. 10 empty, 11 empty, 12 empty, 30 empty, 40 empty, 50 empty, 60 is a force excited state, right? Yeah. So where the energy of set is smaller, initially or now or later? How does energy of set depends on where we are on the axis?
So the earlier on the axis you are, the closer the energies, right? Is that what you're asking?
So at closer to origin, states are denser.
Yes.
Away from the origin, they are sparser.
Yes.
Don't you see it? Denser, sparser.
Oh, okay.
Just repeat it to that we all have it confirmed.
So the closer you are to the origin, the denser your states, and as you get farther away, they get less dense. But how come as you go up, they get more dense?
Because we neglected other degrees of freedom. If we add
Okay.
here plus
The other.
EY plus EZ, they will give an offset, so the origin is shifted. And then we have next excitation in either Z or Y, it will offset by the same pattern for repeat.
Box for the.
It's still a three-dimensional box, but because of incompatibility of dimensions, for some region we scan only one dimension and others do not interfere until we get so far.
So since the one dimension is so much bigger, the energy states for that,
Dense.
that they are denser, but they also decrease faster, creating this shoulder pattern that occurs many times per peak of the smaller box dimensions that also repeat. It's like a pattern containing a pattern.
Yes, other comment, agreement, disagreement.
Can you explain that again?
So since one of the dimensions of the box is much bigger than the others, the energy states will decrease much faster for that dimension compared to the others. Because it's like zooming out on that axis, but staying the same zoom level on the others.
So you're saying
So-
it would be like, say we were drawing another state, it'd be like this, and then it would get like that?
Can I show?
Let me, I'm with you. I'm hearing the comment of James for the first time.
Mhm.
Well, I know that you can come here. I know this idea, but I hear this type of explanation for the first time. So denser, farther, and then starts again. Denser, farther.
So sense like here. So if we have, can I erase it?
Oh, yes.
So let's call it. So since the X and the Y are pretty close, we'll just call this the density for both X and Y.
Yeah.
And the other one, the third dimension, or I guess the other one of the dimensions is much bigger. So with the other dimension being much bigger, we get like, and then. Except the difference between those is much larger than the difference between those. That's much farther zoomed out. So that's like,
Draw it to scale.
like this. So here, we have. And this corresponds to that entire distance, like right there, 5 peaks there, right?
Okay.
So if we wanted, so it's 1, 2, 3, 4, let's give rid of 2 peaks. And this tiny little distance corresponds to all those 4 peaks. So this entire thing is all contained in that tiny little area for the longer dimension.
But so you're saying this axis is at the same scale, but since we changed the length, it kind of squished all those energy states together on that same scale.
Yeah, so since this dimension will decay much faster than these will because of the longer box length in that area.
Yeah.
Longer box length with that dimension. So we have,
And that's because we have L squared on the bottom. So since we increased L for Z, that number is going to get smaller faster.
yeah.
Okay.
Yep. The density states will decrease faster. And since we have all 3 of them, we see it as a weird pattern inside of a pattern. I don't know if that makes any sense. I tried to have.
It's like since we're seeing all of them together, we're seeing the composition of all of the.
Yeah.
But yeah, I see what you're saying.
All together, the decay of one area shows much greater than the decay of the other for the same interval because there's much more length and much more decay over the same amount of time. It's really difficult to explain how it like migrates, but.
Yeah.
Good. Okay, let's thank the team of Garrett and James. Item,
Yeah.
let's do an experiment together.
All right.
So, let's do it on your sheet. Or okay, or you do it right now. So. A lesson from life can describe a pizza box, or huge pizza box, which is as long as it's 270. So run and watch what happens, and then come and teach all of us.
You just want me to run it on?
Yes. Now you see how you can get a Nobel Prize in chemistry. So same composition, same system, just different aspect ratios. Basically.
So for all these, these are all the Jones, so all of them have an area of 1, right?
Yes.
Okay.
And therefore, when you had a three-dimensional 3D, it was so much higher. If you have less, it is a smaller number of peaks per unit energy. Therefore, the theoretical line and computed line are so offset for 0D, 1D, and 2D compared to 3D. Okay.
Is it kind of like the last system, but now we have two that are kind of coinciding with each other?
Mhm.
So then you see a decay of after.
So we have seen agreement and disagreement between theory and computation until some threshold. So probably after this line we cannot trust. But here it is trustability interval. So how you would just verbally describe what you see?
Lot of the density of states, there's a lot of overlap, like a significant amount.
But I had a dream to migrate quantum mechanics course, not from graduate to undergraduate or to high school, but to kindergarten. The quantum mechanics for kindergarten. So how you did it? You would describe this figure for kindergarten students.
There's three major steps in the
Steps. So steps, right?
Yes.
There are areas where density of state doesn't change. It's
Mhm.
constant.
Yep.
Right? Okay. And probably we all are tired. We don't have much time to iterate, but wouldn't you agree that depending on the form factor or on the aspect ratio of the box, the shape of density of states is dramatically different?
Yes.
And looking back on the density of states, one can say whether it was 0 dimension, 1 dimension, 3 dimension.
Mhm.
Okay, let's thank Kaidan. And last experiment, well, it's not an experiment, just let's repeat original setting. So all three sizes of B. Save and run. So it grows, right? And it just slows down how it grows, right? And there is a theoretical prediction telling that it will be infinite growth, but in the computation it goes only up to a certain way. So what do we have as a homework assignment? So we do need 4 figures and verbal interpretation of each of the figures. And we did that, right? So definition of density of states and then just this stuff. Let's maybe quickly go over the code and write comments to each line of the code so that we are confident what is going on, right? So that we are not blind users of black box, but we are educated programmers who can modify the kind. So I'll just start. Remove all error variables. H bar equals 1, M equals 1. It is a freedom for simulation. It's easier to have things in more comfortable dimensions. And by the way, there is a so-called atomic system of units. There are atomic units that you use in freshman courses for like mass of proton equals 1, mass of carbon equals 12. Atomic units of mass, AMU. And there is a AU, atomic units. In the atomic units, not mass of proton, but mass of electron is 1, and mass of not mass, and value of Planck constant is 1. It's done especially by quantum theorists because they want their life easier and they're getting tired to write h bar over m all the time. If those are ones, it is just easier. So atomic system of units. Atomic units. Who is aware of electron volts?
It's the amount of energy an electron gains in a potential of 1 volt.
Okay, good. Everyone is happy? What is the relation of electron volt to other energy units? Is it big or small?
It's very small. It's like 10 to the negative 19 coulomb or 10 to the negative 19 joules, something like that.
But if we measure energy that a single molecule is gaining, like thiophene, upon absorbing a photon, how does electron volt corresponds to the color of the, or to the wavelengths? Like visible light, how many electron volts is in yellow light? A photon of yellow light is,
I don't know. I should check that math. How many nanometers is the visible light? Or
like
yellow light?
660 something. 600 is enough.
You're asking what nanometers yellow?
I'm assuming you are remembering yellow from top of nanometers from the top of your head, and then I'm asking to convert it into electron volts.
I gotta do some math. Quick, give me a second.
So it's 1242 divided by nanometers. 1242 divided by 600 will be about 2 electron volts. So visible light is about 2 electron volts. Infrared is something like smaller than 1, right? UV is more than 3, right? Okay, but James represented the whole class that we know what are electron volts. What are Hartree units of energy? It's not for this class, but later we will use it. So if did you had hydrogen atom for SPD orbitals in like freshman classes or in organic classes, right? So what is the energy to excite hydrogen atom from the ground state to like ionize, to remove yes, ionization energy of the hydrogen atom?
Is that what a Hartree is, an ionization energy?
Ionization energy of hydrogen atom is half of the Hartree.
Oh, so the energy required to ionize 2 hydrogen atoms.
Well, yes. So if one sets up Planck constant equals 1, mass equals 1, maybe something else is 1, and then uses all equations of quantum mechanics to compute ionization energy of hydrogen atom, it will get answer 1/2. But units, if one sets up the simple atomic units, then the unit of energy will be Hartree, which is twice the ionization energy of hydrogen, right? So it's just if one lives in the simple world, if one uses atomic units, one doesn't need to convert anything. There are no constants. Everything is 1. But if one wants to convert atomic units into real life, then one needs a conversion factor between Hartrees and electron volts. So what's the value of ionization of hydrogen atom in the electron volts? No, it's Hartree. Yes, Hartree is 27 electron volts, but ionization of single hydrogen atom, like 13.6.
Yeah.
Okay. And then here it is double of that, right? So it just used as a conversion factor for the easy life. Here we have size of the box in X dimension. I promise I will ask you for the help. I'm just want to go past some challenging parts, and I will speed up X, Y, and Z. And you see that one can reset them. So it's major part where we modify the code, right? To get different results. This one is a range of exploration. So you see, we explore density of states in the range from 0 to 5 electron volts. So we just set it up. If you want different range, you can modify it here. Sigma, it is a width parameter for an individual Gaussian representing a single quantum state. Right? So what we were talking about, right? Each state is represented by a Gaussian function. And to set a Gaussian, we need a width parameter. Here is the width in the atomic units. And then range of energies in atomic units in AU, not grid, but grid. So we, same as in our previous considerations, we chop the area of definition on some grid points, right? And we do not need more than 2000 because of the resolution of our displays. It's rarely like laptops do not have 4K resolution. Like if it is a 4K one, it would take 4000 to use any pixel. Okay, so increment of energy in electron volts, in EV, in EV, increment of energy in car unit. Okay. Now it is a command that you all know about. So we, in hardware units, in atomic units, we just divide by conversion factor. Now energy range, it's same like Lin space. You presented it in our MATLAB session, like setting a range. So E range will be just set of continuous values, finite elements in electron volts. EV. Next one will be finite elements in hardware units. Declaration. So we do define a variable that will contain density of states, and originally we fill it with zeros, but we make sure that the function is have the same length as an argument. So it's like a square, not square, it's a array of the same length as the energies, right? Okay. Now there is something that it's just time is up, so for speeding up, I'll do a little more. In this equation, we run nx from 1 to infinity, and y from 1 to infinity, and z from 1 to infinity. But computationally, we cannot go to true infinity, right? We can, but it will expire our human patience. So here, by the power given to me by administration of NDSU, I set infinity equals 30.
That's great.
Infinity is equal to 30. Or for first summation along x dimension, along x, and then infinity for y is also set to 30. And it's also set 30 along Z. On your own, if you like have time, energy, and curiosity, you can change these numbers and see what will be the consequences.
This is the summation. What is it? Top.
Huh?
The summation, like, it's the top number of the summation.
Yes, top number in the summation, exactly.
Oh, yeah, summation.
Summation, yes. Now, here is the thing that you first three speakers were writing on the board. Equation written by M. Equation written by Anna. Equation written by Spencer. Right? So energy for using like quantized energy along X, Y, and Z. So if any came a little later, this, I believe, was equation written by Wyatt, right? I'm not wrong? This one.
Oh, that was Curtis. Wasn't that
Curtis.
I drew the pizza box.
Huh?
I drew the box.
Oh, okay. Okay. Yeah, okay. Wyatt drew pizza box. Dmitry failed to do blind drawing. Shame on him. So this one was done by Curtis. Okay. Equation written by Curtis. So energy is additive, right? So you add together contributions from each dimension. Now, next one. The height of the peak or normalization, basically it is, we want to compose a single Gaussian line to represent this delta function. And since it is a relatively long equation, it is chopped on several lines. So normalization factor for a Gaussian, y1 over square root of 2 pi, blah, blah, blah. Normalization. And I think sigma should be under square root. It could be an error here on my side, but I just do not want to change it in as we go. After later on at home, I can double check. I think in Gaussian definition, sigma should be under the square root. Normalization of Gaussian for individual energy line. Now, nominator. So it is exactly what we have here. So energy, which is energy range to scan values, minus specific energies that we are specifying by nx and y and z. So it's argument of delta function is plugged into power of exponential. Argument of delta function is plugged into power of x exponential squared. So this stuff squared. And then we combine everything together to get a Gaussian function. Combine VOs two lines to get Gaussian function for one energy level. Okay, so and this is the only little non-trivial thing. So you see, density of states includes summation over all of the delta functions, right? If infinity equals 30, it means this triple summation has 30 times 30 times 30, which will be 3 times 3 times 3, 27, and then 3 zeros. So 27,000. So we need to add together 27,000 of Gaussian functions, each of which has a peak at different point, right? But we need to add them. And as cycle goes on, we can add only one peak. So we add one more peak to our definition of DOS. Add one more peak to the definition of DOS. So if we would limit summation nx from 1 to 1, right, in each dimension, then we will get only one peak, only the lowest peak, right? But as we increase more and more peaks, we have a distribution representing the whole system. Okay, close loop. Close all loops. By this time, we do have data ready. Data are ready. Sorry for not inviting you to type this. I just want us to finish in time. Now we, along x-axis, we have range. Along y-axis, we have density of states. So there is a first line, and then we do just e range to the power 2/3. So on Monday, we will prove that for three-dimensional large box, density of states escalates as power 2/3. Right now, we just put it as a theory prediction. So computed and theoretical lines. And then those are just labels and legends. Labels, legends. All clear? Any questions on this? Okay, one more thing that you will enjoy. In some sense, I'm stepping on my own tail and making Monday lecture a little less spectacular, but I'm very impatient and I want you to do something that I'm confident you will like. So let me close this one and open script DOS_all_ version 5 and run. So just invite you to run and watch. Do it on your own computers and we will discuss it as we go. So this script, which is a little longer, will generate a movie that I invite you to complete, upload to YouTube and send me the links. What do you see? How do you interpret it?
I see the energy density increasing on the graph, probably because we're increasing the size of the box.
Okay, great. Yeah, thank you.
There is a box. Oh my gosh, there's a box. I didn't see the box.
Tell us.
It's the box that's shown in pink. That's the box that's changing, and that's the energy density.
Tell the information to Wyatt. He's very curious. What is the box's form factor? How it is shaped?
Well, why the box is like it was like your ski box, and then it's starting to turn into your pizza box.
Okay.
No, why not with it?
Run the segments.
Yeah.
So cute. This figure on it says.
Okay. So did everyone got the script running or something?
Mine doesn't look like that. Mine's just stationary.
So who has stuff like that and who doesn't? I know that Garrett has things like that. Did anyone? Okay, so the email contains the file cube.m, is downloaded and so that it is located in the same directory as those. You did it? I did that. So programmers of 21st century are very lazy. They're lazy to write everything themselves, and they're lazy to put everything in one file. They typically borrow pre-made little subroutines for little things and put them in the same directory, and they just call subroutines, like orchestrating little helpers. Okay. Like. And then when it is done, it should create it should create a AVI file in the but you should have the plot cube in the same direction. If you look into my email, there is one more attachment, plot cube.m.
All right.
Oh.
I'm not.
You just download and have it after plot cube is installed, downloaded, you rerun this code. No. The script DOS all is calling for plot cube, is requesting plot cube.
Right.
It looks like we all are getting tired.
What gave it away?
Well, those who were not drinking coffee definitely are getting tired.
Not me.
I'm not getting tired.
So I'm going to upload, share with everyone. Huh? It finished on everything. So I'm just going to upload and send everyone the link and asking you to do the same. And then I promise to put likes and maybe even comments.
Be close there.
Just slowly getting bigger.
Did you?
It's quite nice.
Those?
I don't know.
Yeah, it feels so good. Probably good to connect your computers. My computer from fresh.
It's
Oh, God. You'd get to a certain point and it'd be like a plastic.
Yeah. What is baby? You guys. Where are the Oh, chapter 10? Yeah. Oh shit, I forgot about that. The very last one, I just can't. Is it chapter 10 you guys are on? Yeah. Oh, also, so what did you get on the most recent biochem quiz? I got like 11. I'm struggling in biochem, bro. 11? Wait, like 11 out of 15, I think so. You don't tell you which ones you get wrong? Nah, you have to wait. Wait, it doesn't even tell you which ones you got wrong. No, you have to wait until after it becomes graded for everyone else. So like you have to wait until tomorrow, Wednesday, or whatever. No, you should be able to check because it was due Wednesday. You should be able to check them. Oh, yeah. So, is biochem easy to you guys, or you guys like that?
I'm here for
It's not super easy, but I do a lot of reading. I read the textbook. Yeah.
I just said I'm.
So the key is to reading. Yes.
I mean, it is my major, so.
You don't have to do that. I'm just trying to figure out like all of that. Why I suck at it. I can't
Yeah,
focus
it's
on
hard.
reading the
It's a lot of
textbook.
specific information. Especially when it seems like that's how he likes to format it, is like.
Is it done? Oh, yeah, it's done.
The things that are worth the less points are more specific. But the more points the word, the less specific questions are. So I don't think we
Please
have to worry about exams.
upload your videos and share the link.
Just gotta do it. Yeah.
They're specific. I can get one right every once in a while, but guessing, it's like, oh, that kind of makes sense, but like.
Yeah.
Yeah.
But reading the textbook, if you like spend the time and actually like understand every single thing that textbook is, you can go through the reading assignments with that. I don't
So
know.
when you get it uploaded, it should go a little quicker.
Why does yours go so fast?
Yo.
Well, you can do increase argument in the pause command, and then it will go a little slower. But it is not computation; it's just plain already uploaded stuff, and it just shows continuous change from small box to ski box to pizza box. You see this feature, and then it how this things form the steps, right? And then multiple, when it gets thicker, multiple steps form this inverse parabola. Yes, please, and just wait until it is done. Do not stop it. And when it is done, it will automatically create the. Yes.
It will automatically create what's it?
If you, James, what would it create? She just told it.
So it should say scan DOS V12 under documents, assuming you kept everything as the default file paths. Go under your present working directory or PWD, and it should say the scan DOS V12 in there, and then you can click on that when you're uploading it to YouTube. 26 seconds.
Right.
So it turns out, no, basically an MP4 file
Was
is
it
not.
so all the time, or it's
That was it, maybe I.
stored at some?
Maybe it's so I can restart it.
Okay. And
So what is,
if
it's,
you are tired and time is up, you can.
let's see, it's,
do it.
I had no fun on the radio, so like. This is no.
It's getting so old, it's still changing. So if you think that your computer is giving you unfairly long time and you want to restart and speed up, one can decree that infinity is equal to 20, and then it will be substantially quicker. 20 will be 8,000 instead of 27.
You want me to, you want me to just reply to the email you?
Yes, with including like the link.
Yeah. Okay, so if it's done.
If it is done,
What do I do here then?
go to your YouTube.
Not.
You can type PWD here. So
Okay, yeah.
Alright.
Go to sales documents, MATLAB. Then go to Google, type YouTube. Click on the little plus.
Yeah. We're replying to the email, right? I just sent it. Oh, okay, wait, James, did you send a reply to that email you sent us?
Just navigate.
Oh, I just sent him one. Yeah, either way.
Probably not as cool as mine.
Wow, okay. That was mean, Gary.
Oh, yeah.
They're the exact same.
Ah, James, okay.
That was a couple jokes.
With like.
You just go.
Not ready for it.
Impressive. Thank. Come on. Okay.
He's so fucking. I think I was left hysterically. Wait, we have to email this to him.
He's just.
Here is my video.
Yeah. Little bugs.
Mike.
Pretty rad. See the description.
Comments are turned off.
Oh.
So many people want to express admiration so that you are tired of them. Okay, like is enough. And I think I have subscribed, yes.
Yeah, it's smooth. It wasn't smooth up there, but it's smooth on my computer, I guess. Ish.
Books. Spencer.
Just a better computer, I guess. I don't know.
Yeah. Evidence.
I am so happy to see this movie.
Stupid, you know?
Not stupid, the smart movie. Very help.
I made that email when Pokemon first came out.
Yeah.
My password for my other.
Yeah.
So
Like,
those.
wow, it works.
Do you want it to your Gmail or to?
Gmail is better, but I read both. I just read Gmail a little more frequent.
Okay, I think I said.
How many times?
Sure.
Ski pizza. Why is there a ski pizza? No, your video is age restricted. I'm not authorized. Okay, let's see about this one. Oh, this one is work. This one works. Okay, better. Let's try to open it. No, this is when I have some. But of course, I can put like to myself as well.
So many subscribers.
Let's. Okay. It was what Kaiden dreams about. Not only Kaiden. Okay. Who else? Inbox. No, let's go to another. Oh, something is already working here. Okay. Garrett has already got his. Oh, he sent to both.
I didn't know.
That's fine. You can get 2 likes and 2 comments from my different identities. Video may be inappropriate. Okay, sorry. I'm inappropriate. Probably it's already locked. You got, okay.
There's like a.
Oh, that is a nice video. This is how people traumatize their children.
Video.
These videos.
Right.
These videos, yeah.
Help.
So
Next.
one kid looks at this, it's like,
Generation.
yeah.
Once they reach
And of course.
stage.
Yeah.
Okay.
Commented. I said this is what get into.
It's
It's so true.
Hmm.
Why do I have
Life's
to?
wordy.
And you can loop it so that it doesn't stop. So, congratulations to all
Jordan.
physical engineers
No, he didn't go to Concord. He went.
of the world for the Nobel
I think
Prize
once.
being awarded to one dot
But he eats most.
research.
So obviously it's the easiest way.
This video is
But like,
exactly about that.
keto.
Interesting.
So not like bread.
But he can't have like super high salt content. He said he would eat vinegar, salt and vinegar chips. He would pass
Like pass out, or like.
Pass out.
Like it would be hard to stay awake from like.
Not just with the really conscious.
I don't know if I.
Who else? Let's check here. If any, did you send? Did you were able to complete it?
Oh, God.
No? Okay, let's quickly check and then.
Right under transfer.
Comments for the other one. Can you pull those up so I can? Oh, that's.
Yes.
That's terrifying.
Yes.
Griffin. You don't like Hanasa? Why not? Huh? My old boyfriends.
Okay, you need to wait until it is.
He runs up the name out of me.
What was your?
That's pretty cool.
Yeah.
You- you-
Was it 8? It's not too far.
Yeah. Just one.
Just kidding.
Awesome sauce.
Happening.
That was awesome possum.
There's nothing there.
That was so awesome possum. That is that. Games.
Huh? Where's this?
Yeah, bro. The dark chocolate stimulates your brain. Brain function. That's good.
It should- Yes, here. So you just need to wait until it is done.
Yeah.
And when it will be done, there will be files that you need to upload to YouTube.
Where's the?
So where is the camera? Probably there. So let's turn to the camera and tell that meeting is done. Many thanks to everyone. Yeah. So thank you for your investment of the time to do this class and the lab, and looking forward to see you on Friday, right?
Oh, God.
No. Don't say that to me. Why? No. Don't worry, I got it. I was worried.
You like dancing, Dimitri, or not?
No.
No.
No dancing.
When I was about 5 years old,
Yeah,
my parents brought me to like choir,
okay.
and the instructor noticed that I do have medical understanding, and but he didn't want to offend me by saying this. So he like I was like to the side, and so I was thinking very loud and energetic, someone with this. He gave us time for number 5 and drinking the dances. But I survived till the one. Wasn't. Yeah, of course. Did you?
I never took dance, but my parents had me take piano lessons until I was like 15. I was in band and jazz. But, no real dancing. I did that more to be funny.
We can, well, I do not promise, but I probably can find online, dance your PhD, maybe like dance your undergraduate exam.
Perfect. I'll do it.
Yes.
That'd be fun. Interpretive dancing.
You start to do the doggy.
Okay, I think I got all the lines commented here. Yeah, you got, I'm renamed my YouTube videos. Everything should be good. Okay. Oh, yeah, I forgot I didn't run my. I'm gonna go wash my hands and then I'll be back to grab my computer.